Welcome to Stat 479, Lecture 5. So today we're going to dig into gradient descent a little bit more. So just a reminder that homework 1 is due Thursday, September 24. So today we're going to really dig deep into the convergence properties of gradient descent for solving least squares. And this is something I started to talk a little bit about in the previous lecture. We're going to dig into the actual algorithm of how you implement solutions to solving the linear system that minimizes the least squares. And this is something that will be useful because you're actually going to implement this in your homework. And so some of the ideas that we learned today will be quite useful in terms of just seeing things like how to choose step sizes and how to choose starting points and that kind of thing. That'll come out of the analysis and math that we do today. So just like always, I like to kind of start with the general framework just to ground everything again and to remind us of what we're really doing in the bigger picture. So right now we're still in the scenario where we're looking at multivariate linear regression. And as I mentioned, this is a very widely solved problem. So you might be thinking we're spending a long time on this, but a lot of what we learn here is there are fundamentals that we'll build on throughout the course. So the data here again is there's P, it's multivariate linear regression. So there's P variables and one response and there's N samples. And so you can write it conveniently in matrix notation where X is an N by P matrix and Y is an N-dimensional vector. And then once again, you can express this as a linear model where B is the parameter of interest that we're trying to find, and epsilon is the noise variable. We're not going to focus too much on this linear model today because we're going to really dig into the third component, which is the algorithm. So in terms of the algorithm, the way I've expressed it so far is that we're trying to minimize some objectives. So we've spoken for the last couple of lectures about minimizing least squares. That's one way to find a solution to B. And then the other one that we spoke about last time was maximum likelihood. So this is only really something we naturally do if we know that the noise is multivariate normal. And we spoke about how that reduces to solving a quadratic, to minimizing a quadratic as well. Okay, and so today we're going to focus explicitly on finding this B hat. So as we know, it's the solution to a linear system. So you could easily just say, oh, well, that's easy to do. All you have to do is kind of invert a matrix. And that's true. But we're going to dig into the specifics of how you can kind of invert a matrix. I spoke about, there's whole books and whole courses taught on the books written about this and whole courses on how to do this because it's so important. So we're going to just spend a little bit of time talking about one method to actually invert this linear system. So we're going to focus on the algorithm that we mentioned in the previous lecture, gradient descent. And the reason why I like this is because it's so widely used. And it's just, if we understand how gradient descent works, that often tells us quite a bit about how lots of other algorithms are going to work as well. Okay, so just to remind everyone about gradient descent, some of you may have seen it before if you've taken some kind of optimization course, but some may not have, and that's okay. One of the things you're going to do on your first homework is to just implement gradient descent. And as you'll see here, this update equation is very, very simple. So this is something that's really worth remembering because it's something that is very useful and it's a very easy thing to implement. So for gradient descent, you're assuming that you have some differentiable function. We're in the multivariate setting, so this is a multivariate function, and we're assuming it's differentiable. And so the gradient descent update is simply bt plus 1 equals bt minus this alpha t times the gradient. And so there's two things that are important here. So the f is given to us, but we have to choose these step size parameters, and then there's also a starting point to be chosen. So let's look at it in the So in the least squares case, let's look at what this boils down to. So here we have this quadratic objective here. So the gradient of this objective, using again matrix notation, the 2 comes out and is included, like you multiply the 2 out, and then so the half times 2 becomes 1, so that disappears, and you just get you using matrix vector notation, it's just x transpose times xb minus y. And a good check to do is to always make sure the dimensions match up, and they certainly do. X is an n by p matrix, so x transpose is a p by n matrix, and these are both n-dimensional vectors. And so the gradient should be p-dimensional because the function is a function of p variables. Okay, and so we saw in the previous lecture that when we write out the gradient descent update, this means that we have okay, and we can expand on this a little bit further and just write this out as okay. And so this is the gradient descent update for least squares. And so, as I mentioned, there's a couple of key questions. One is, how do we choose the starting point B0? And how do we choose step sizes, alpha t? And probably the most important question of all is that so does solution of gradient descent converge to what we want to? I mean, I've kind of pulled out these we've pulled out these this expression, and it seems to be kind of pulled out of thin air. We want to say that we have, we know that the solution should satisfy x transpose x beta hat equals x transpose y. So as t goes to infinity, we should have that, we would hope that this is true, that x transpose x bt should converge to x transpose y. So just to give you a little bit of intuition about gradient descent and why you might expect it to converge. So we have that and so what we can see is that if gradient f of bt equals 0, you can see then that you'll just get that bt plus 1 equals bt. And then, so therefore, that'll also implies bt plus 2 equals bt plus 1. And so we have convergence. So as long as step sizes and starting points are chosen well, we should converge to a, a zero gradient point. Okay, and so that's essentially in a nutshell the intuition behind why gradient descent you might expect it to converge. But today, so today we're going to address those questions explicitly for least squares, and the reason why I'm going to go into this analysis in a fair bit of depth, and the reason for that, there's a couple of reasons. One is that for least squares we get a linear system, and that actually gives you a very nice linear update where you can actually write things out explicitly and really understand what's going on. And then because we're going to use gradient descent so widely, a lot of the intuition we learn from this will really be applicable. And from your perspective, it's going to be really useful to follow this analysis, because on your homework, you're going to not be required to do that analysis, but you're going to be required to implement gradient descent, which means you're going to have to choose step sizes and also starting points for your various scenarios. And this analysis should give you some idea of how you choose those. Okay, so remember that we started with okay, and so we can we're going to kind of play around with this and see that we can actually write this out in a very, very nice way. And so what, the first thing we can address is, if we just write out a few steps. Okay, so you can see that we're kind of getting recursions that we can see that what we're eventually going to get if you kind of write this out is that okay, and so so what we're going to get is that our BT, if we keep imagine running this out, so I wrote it out for 2 steps just for you to get an idea of what's going on. You can see that B1 obviously depends on B0 and X transpose Y, B2 depends on B1 and X transpose Y, and B1 depends on B0 and X transpose Y. So we can clearly see that BT is going to be an expression where it's going to be some equation in front of B0 and then some other expression in front of X transpose Y. So we want to find expressions for both. And so we can hopefully see, we'll see that this expression ends up, not being too complicated, although it might look quite complicated when we consider it, when we look at it right now. And the third question that we're interested in is, so that's the first question that we're interested in. So what we're going to actually look at is so we're going to kind of write everything in terms of X transpose X here. So sorry, let me. If we sorry, let me just go back a bit there. So if we express we're going to see that it's going to be very convenient if we actually express everything in this space where we multiply by X transpose X, because that's really the function that we're going to be interested in here. So we can clearly see that we're going to get that this equals sorry, let me do this again. Sorry, let me do that again. It's because the function that we're interested in is really xb. We can write this out as and so what this is going to be make our expression a lot nicer, because then now we can write this out as okay. And why this is a very convenient and nice thing to do is you'll notice that we can write this, we see this alpha t xx transpose in front of the xbt and the y. Okay, and so now what we can do is this allows us to kind of express this gradient descent update in a very convenient way. Because we can now just kind of write this in terms of some expression in front of xp0 and some expression times y. And in this space, if we um, so now when we do this analysis, so we can show by induction what 1 and 2 are. So to find this first expression, okay? So we can express this like this. So what you might guess is that we're just going to kind of get this product here of these matrices all being multiplied. So I'm going to use this definition that ST okay, and so it's going to actually work out really nicely that the first term is going to be ST, and the second term is going to be I minus ST. So we're going to claim that okay, where okay. And again, we're kind of getting into the mathematical detail here quite deeply. The reason for that is because I just kind of want you to see how it's done once, because it's going to give, and the final result is actually going to give us a lot of insight into understanding, you know, how to choose these step size sequences, and how to choose a starting point, and whether it makes a difference or not. And this is going to be useful in your implementation, not just for this, but we're going to implement gradient descent for other objectives as well in this course. Okay, so while we're going through the math, I mean, the math might seem a little bit heavy and tedious. Just sort of keep the big picture in mind here. So we're going to do a proof by induction. And by definition, it's clearly true for t equals 0 and 1. We've kind of written that out already. So for t equals 0, we have that xb0 is just st times xb. So I guess we should be more specific that, for it's clearly true for t equals 1 here, because t equals 0 is a choice, so t equals 1 is really the only thing we have to check here. So we know that xb1 is equal to s1 times xb0 plus I minus s1 y. So let's check out what that is. So for so that means you plug in t equals 1, so that equals s1 is just going to be I minus alpha 0 xx transpose, and that's exactly what we get. So remember that the first update just said that we get I minus alpha 0 xx transpose xb0 plus alpha xx transpose y. Okay, so now let's as we know by induction, we know that if we can just assume true for t, so we assume that it's true that I minus st times y, and now we want to prove for t plus 1, and once we do that, that'll mean that we can prove the result for all integers t. So we know that the gradient descent update, it's an iterative update, so it makes sense that this proof's going to use some form of an induction argument. We know that by definition that's going to be So we know that the gradient descent update looks like this. And then we know that, or we've assumed that xbt equals sd xb0 plus I minus sty. And so therefore we know that so all I've done here is just write that out. So now we've plugged in xbt here. Okay, and then remember that st by definition is this. It's given by this kind of this matrix where you're just multiplying this term. You're kind of multiplying this term, and so we can see that this. So that's the coefficient of xb0. And then for y, what we're going to get is okay. And so we know that, so therefore we know that also st plus 1 is given by this expression, where now we're taking the product up to t rather than to t minus 1. Okay, and so we can see that clearly the expression in front of of xb0 is just st plus 1. And then for y, we can kind of add all the terms up. So okay, and so we can see that this is clearly going that this is going to give us some minus st plus 1, because this term gets multiplied through here, and then and so you can see that the alpha t xx transpose cancel out, and so therefore we have that okay. Therefore we have that the proof is complete. And then we can conclude that for all t we have that xbt equals st times xb0 plus I minus sty, where this matrix st, which we're going to look at in a little more detail soon, is the product of this this I minus alpha k xx transpose. So let's return. So that was sort of a lot of math to take in, but we're going to see what the point of that is, hopefully, when we look at when we return to our questions. So how do we choose starting point? And that means choosing b0 or xb0. How do we choose sequence of step sizes? And the final thing is, do we have okay, and so recall that what we have now is an explicit expression for this xbt in terms of xb0, which is a starting point, and y. And so note that if this matrix st converges to 0, as t goes to infinity, then we have so then in that scenario, then we have that xbt converges to y, and effect of xb0 goes away. So so if this matrix, which is, so this is n by n matrix, and so we're talking about zeros and the whole matrix goes to zero, then we have that x transpose x beta t, which is one property that we like, and xb0 does not matter. Therefore, any starting point is okay. But note that how fast you converge may depend on the starting point. But by and large, in this particular setting, the starting point shouldn't really matter too much in this particular case. And certainly for other objectives, the starting point will matter, and we will talk about that at various points. But when we have this nice linear system, the starting point shouldn't matter as long as st goes to 0. So we've kind of touched on two questions here, which is, do we get the right convergence? And I've said we do as long as st goes to 0. Which is this matrix. And now we've addressed another question about the starting point B0, that it doesn't really matter as long as st goes to 0. So then the question is, so how do we ensure st goes to 0? And so remember that so we have that st is equal to this n by n matrix, which is the product of these T matrices that you're multiplying together. And so this really gets to the question of how do we choose step sizes? How do we choose step sizes? These alpha t's for t going from 0 to infinity. Okay, so so the intuition, we're gonna try to be a little more rigorous later, but the intuition is that this matrix I minus alpha k xx transpose should be between the identity matrix and between 0. Since xx transpose is going to be positive semi-definite. Okay. And so this is referred to, it's kind of a contractive. So so you're multiplying several matrices together with eigenvalues less than 1. And so this ensures product goes to 0. Okay, and so we kind of need to ensure that we want to ensure that this matrix is between 0 and 1. And so one condition that that we want is to ensure that alpha k should be less than or equal to 1 over the maximum singular value of XX transpose. To make sure that all of the eigenvalues stay, or I should maybe use the term eigenvalue. This is the maximum eigenvalue of XX transpose. Okay, and then the other thing we obviously need to ensure is that alpha k is bigger than 0. And this should be true for all k. But how do we ensure that st goes to 0? And so to do that, I'm going to kind of use an approximation here. Or not an approximation, but an inequality. So I'm being a little bit loose with the matrix notation here, because we're taking exponentials of a matrix. You can imagine that this is almost the same as taking exponentials of a number, because you can essentially just take an eigenvalue decomposition and then diagonalize everything, and everything's valid. So the way to think about why that's true is that this is true since if you, for a number, you can check that by kind of a simple Taylor expansion or inequality, you can show that 1 minus delta is less than or equal to the exponential of delta. And why this is nice is because that just tells you that st is less than and because it's an exponential, we can bring the product inside the sum. And we want to ensure that st goes to 0. We need whatever's inside that exponential to go to infinity. So we need this sum of step sizes to go to infinity. So to summarize, okay, and so we have these two conditions, and these two are going to be sort of useful when you think about how to choose your step sizes for the homework problems. So just let's talk through this a little bit. So one ensures each step is not too big. If you pick a step that's too big, you can kind of overshoot the overshooting minimizer. So basically, like if you choose a step size that's so big, you might actually kind of go like, you could imagine going to like overshooting the minimizer and going to the other side of it, and then you'll never really converge. And then the second condition ensures that step sizes are big enough collectively to ensure you travel far enough to reach minimum. So if you choose a sequence of step sizes that's essentially so small that you kind of only that your steps are so small, you may never actually get to the minimizer. So you kind of need to make sure that your step sizes are small enough that you don't actually overshoot the minimizer. But you also need to make sure that they're collectively big enough, which means that you can eventually, if you're far away from them, no matter how far away you are from the minimizer, you'll eventually get there. So a very common example is, and one you could certainly implement for your homework, is that alpha k equals constant, where that alpha is like some number Okay, so as long as you pick that constant to be not too big, then a perfectly valid thing to do is to choose a constant. Clearly, if you sum up a constant, it's eventually going to go to infinity. Therefore, you can that ensures that the second condition is satisfied, and as long as that constant isn't too big, you should be fine. And that's a fairly typical choice for how people decide like how to choose step sizes for gradient descent. So the conclusions that we draw from this for linear systems are that this is for least squares. So B0 doesn't matter as long as alpha t is valid. So it's a valid set of sequences. So we get convergence as long as as long as these sequences is as long as the question of convergence is also true as long as your sequences are valid. In you mean you can't let t go to infinity, or I mean, you have to stop eventually, obviously. But stop when difference between b1, bt plus 1 and bt is very small. Okay, so this is, you're going to implement this in your homework, and that's essentially what you need to determine. So you need to determine you know like the step size, the valid step size sequence. So clearly the choice of step size is the most important decision that you have to make. And then the other, and then your starting point doesn't really matter too much, but the closer you start to the minimizer, the better. And you obviously can't run an algorithm forever, but you can stop when you're starting to get so close that the steps you take are basically making like such a infinitesimally small improvement to your results. And in your homework, you're going to do this when we have both least squares, which I've just done here. So that shouldn't be too difficult. And maximum likelihood. And you'll see that when you have maximum likelihood in the Gaussian case, you're just going to get a different quadratic update, which isn't going to be kind of exactly the same as least squares. And another question to think about is, why does the starting point B0 not really matter in terms of, you will always converge. Is quadratic. So because you have a quadratic, is a quadratic, and therefore f is what's known as convex. And so this is going to be something that will come up a lot throughout the course. If f is convex, minimization becomes more tractable. And in fact, this is actually strictly convex, and this is the nicest. Basically, quadratics are the nicest kind of things that you can minimize. It becomes tractable since f has unique minimum. And what do we mean by convex? So convex means that the Hessian matrix, this is what's called the Hessian. This is basically greater than or equal to 0. Okay, and so let's think about the Hessian matrix that we have here. So remember that Okay, and so now if we imagine taking the next derivative, we get that this Hessian matrix is X transpose X. Okay, and so clearly, because we have a quadratic, so therefore we have that F is convex. Okay. For convex functions, starting points usually so, and if you want to, if you're kind of interested in this a little bit more, so convex functions kind of basically just look, something like this, sort of like a quadratic, that essentially they just go down and go up, and you can sort of see that there's like unique minimizer here. And there's whole books written on convex optimization. So we're trying to minimize convex functions. And so, we're going to see that actually come up in the next section, where we talk about when we talk about going past linear models to generalized linear models. But I just wanted to kind of touch on it here. And this has been a pretty heavy kind of optimization-y kind of lecture because we're focused on gradient descent. And as I mentioned, that's because this algorithm is going to be used a lot in this course, and it gives us a lot of insight into what's going on. So just to recap, so in terms of for gradient descent for least squares, so we derived explicit updates. And this is something we're not typically going to be able to do. We can only do in this case because we have a quadratic objective. The gradient's linear, so the update equations are linear, which makes everything nice. So we derived explicit updates for each iteration, and then found step size conditions to ensure convergence. Okay. So yeah, that's it for today. So we're going to just round off our discussion on linear models. We've covered quite a few different things for linear models. We're going to kind of round off that discussion in the next lecture, and then move on to the next sort of big topic, which is generalized linear models. Okay, thanks. That's it for this lecture.